In this lecture, we're going to look at searching, in particular the linear search and the binary search. So as we talk about searching here, just a quick little definition. It's the process of locating a particular element within our data structure. The type of data structures that we may have may be an array list, it could be a linked list or a tree. The examples that we will be using in this lecture are going to be dealing with array lists, and in particular just a list of data, which can be an array list or an array. By way of reminder, our steps in searching a list: we have our initialization, we have our iteration through the list where we're going to be searching and updating information as necessary, and then once we've iterated through our list, we're then going to return the results. I have a method here called getMinimumGrade. It's going to exemplify those three steps, and it's going to be similar to some methods that you've already written back in CS6311. So here's our initialization. We're going to be getting the minimum grade of our very first student, and that's going to be our initialization. Then we have our iteration where we're going to iterate through each element in the list. That's this for each loop here. What I do then is for each student, I get its grade, and then I see if its grade is less than the current min. If it is, then I'm going to update the current min. So that's our update during our iteration. Then once I have iterated through the entire list, once I drop out, then I do my returning of the result. How long does it take to search an unsorted list? Well, it depends on the number of elements in the unsorted list. The bigger the list, the longer it takes, because we must visit every element in the list, in particular if we're searching for a min or a max, because we don't know where that minimum is going to occur in the list. It could be the first element, it could be some middle element, it could be the very last element. So if we're searching for a min or a max, then we're going to have to go and visit every single element in the list. So if we have 100 elements in our list, we're going to have to visit all 100. If we have 1 million, we're going to have to visit all 1 million. Now, let's say that we're searching for a particular element using a search key, that I want to find a student named John Doe in my list. And once I find that, then I can get out of my search. So in the best case, when I start iterating through my list, John Doe is the first student in the list. So I visit the first one and get out. And the worst case is the student I'm searching for in my list is either the last element or the student is not found in the list. The only way I can know that is by visiting every single element in the list. So if my list has 100 elements in it, I'm going to have to visit all 100 elements in there. So a list of size n, it's going to take me n comparisons to do that. This process of iterating through a list and visiting each element in the list is known as a linear search. A linear search works well for small lists and unsorted lists. However, it is very inefficient for large lists because we must visit every single element in our list. We know that we can take advantage and probably speed up our search if our list has some order that we know about. And so this is where we have sorted lists. So if we know that we have a sorted list, if we're searching for the min or max element and it's sorted in ascending order, then I know the min is going to be the very first element in the list. So I just go to the first element, get that, and that's my minimum value. Whereas the max is guaranteed to be the last element in the list. So I just go to the last element and get that. So in these, I only had to visit just one element each. Now for searching by a search key, that's a little bit different because we don't know where or we don't know how exactly our data is structured in there. But we can still use the knowledge that we have a sorted list to help expedite the search and cut down our search size. We do this when we look for a word in a dictionary. For example, if you're looking for the word giraffe and you turn to the M's, well, you don't look past the M's at all. You turn back towards the front of the dictionary. So you're eliminating some of your search, the words that you're searching through, just because you know that the dictionary is sorted. What we need to do then is come up with an approach to decrease the size of the search on each iteration. And we want to decrease it by as much as possible. And so the best way to do this is to go to the middle element of the sorted list so we can eliminate half the list. Then we compare our key to that middle element in our sorted list. If the key is less than that middle element, then we know that the element that we're looking for is in the first half of the list, so we're going to eliminate the second half of the list. If the key is greater than the middle element, then we can eliminate the first half of the list and just search in the second half. And then if the key happens to actually equal that middle element, then our search is over and we can just return that middle element. One question we have to ask ourselves is, how do we determine the middle element? Well, one, we can use integer arithmetic, because we know that we're going to have always a whole number, an integer that's going to represent the size of our list. So I can say our middle element equals a floor of n divided by 2, where n is the number of elements in our list. Now we can take advantage of integer arithmetic to automatically get rid of any fractional portion. So here I got integer n equals 9. Integer middle equals n int divided by 2. 9 divided by 2 is 4.5. It truncates the result, and so we lose that fractional portion, and so we're going to get the middle equals 4. Let's say that we're searching in a certain portion of our list. We need to be able to find the middle element between our certain set of indices. So what's the middle element between 11 and 20? We can use this formula here where the middle equals low plus high divided by 2. So 11 plus 20 equals 31. 31 divided by 2 is going to equal 15 using integer arithmetic. So that's how we can calculate the middle element. Here, I'm going to do a little example. We have a sorted list of animals here, and we're going to be searching for the word jaguar. So the first thing I do is come in here. I got my low index, my high index. I calculate my middle, which equals 4. So I come in here and now compare jaguar to hippo. Does jaguar equal hippo? No, it's not. It's actually greater than. So I can come in now and eliminate the first half of my list. Now I'm going to search a smaller list. I'm going to search the second half of my list from indices 5 to 9. When I do that, I'm going to get the middle element to be 7. Then I can compare jaguar to parrot. When I compare jaguar to parrot, jaguar is less than parrot, so I can eliminate the latter half of my list. So I eliminate that. And now I'm going to search on this smaller list. When I do that and I come in, I'm now going to determine my middle index. I'm going to get 5. I compare jaguar to jaguar. I have now found it. So I can return my middle element or the index of that middle element, whatever I need. So this process here of searching by going to the middle element, eliminating half your search field, searching in the other half, is known as a binary search. I've provided a link, and there's actually an example code in your book on ways to implement that. Now, fortunately, most often you're never going to need to code it yourself, because if you're using any of the Java collection classes like an ArrayList or array, then what you can do is implement the comparable interface, and once you've done that, you can call collections.sort to sort your list. When that is completed, then you can call the collections, and there's actually a binary search method. Please know that this binary search will only work on a sorted list, so you have to guarantee that it's sorted, and a good way to do that is by calling collections.sort. How long does it take to search a sorted list? To find the min or max value, we know that it's the first or last element in the list respectively. But if we're searching by a search key in our list, every time we're cutting our search field in half, and this is going to provide us some significant savings. When we're searching this, in the best case, we're going to the middle element, and we could get really, really lucky, and the first element that we compare to is actually our search key, and so then we're done with the search. However, when we are doing comparisons, or when we're trying to determine how long our algorithm is going to take, we always want to look at the worst case. And the worst case here is the element's not in the list. So we have to keep halving the list and halving the list until we get down until there's no longer any elements in our list. If our list is of size n, it actually takes log base 2 comparisons to keep cutting our list down. What is the running time of our algorithm then? Well, it's based on the input size. And what that running time is going to represent is how long on average, or particularly in the worst case, is it going to take for this algorithm to complete. So when we're doing searching, what we're interested in is how many elements do I need to compare against before I'm able to find my element. So we want to know in the worst case what that's going to be. What are some running times of some basic algorithms? If we're going to visit each element in the list, this here is known as a linear search. And we can say that in some different ways. We can say it's an order n algorithm, where n represents the number of elements in our list, and that we're going to have to visit all n elements. Or we may write it as, this notation here is big O, or grows like n. As n grows, it grows with n. If we cut the problem size in half with each iteration, as is done in the binary search, this is known as an order log n algorithm, or a big O of log n. Please note that LG is a shortcut for log base 2, and it's a common notation we'll use in computer science. Now, if we keep doing something the same amount of operations regardless of the size of our list, regardless of how big n is, for example, if we just want to go to an individual list element and set that value to 0, well, that's just a constant time because we can jump straight to that particular element. So that's what we call a constant time algorithm, or a big O of 1 algorithm. Does it really make a difference? So what I've got here is a little graph, and what this is showing, this is n. So if n is, we have 16 elements up to over 1 million elements. If we're doing a linear algorithm, that's a big O of n algorithm. How long is it going to take? How many comparisons am I going to need to do? Well, for 16, I'm going to have to visit all 16 elements. For 4096, I'm going to have to visit all 4096. For 1 million elements, I'm going to have to visit all 1 million elements. Now, if it's a log n algorithm, coming down here, for 4096, I'm only going to have to visit 12 elements. There's significant savings from visiting 4096 down to 12. For these over 1 million elements here, if it's linear, I'm going to have to visit all 1 million elements. But if it's a log n, as is done in a binary search, then I'm only going to have to visit 20 elements. Again, they're huge savings. So log n algorithms are significantly faster than linear algorithms. Linear versus binary search. If n is small and our search is done rarely, then the linear search is better. I know that may sound a little bit weird because here I just showed that a binary search is always significantly faster than a linear search. Well, the key to remember here is that we have to make sure that our list is sorted, and it does take actually some significant time to get an unsorted list to a sorted list. If n is small and we're just going to search on occasion, then a linear search is better. Linear search is easier to code, but just because something is easier to code doesn't mean that that should be a determining factor on what we implement. The binary search is better if we have to do a lot of searching, if n is really, really large, and the data is relatively static. Because if the data changes for the binary search to work, what that means is then we've got to come in and resort that. It does take significant time to sort a list. It's actually a big O of n times log n algorithm, which is greater than a big O of n algorithm. What type of list can we use binary search on? We need lists that have a direct access to any element in the list. So the array list and the arrays are lists that we can use a binary search on because we can jump to any particular element. That is the end of this lecture on linear and binary search, and you can read some more about this in the reading exercise for this unit.